Taking a photo of a scene is a great way to capture a memory or a moment. However, photos only provide information in 2 dimensions. But what about a camera that could capture a scene in all 3 dimensions, even from hundreds of meters away? Techniques for looking at scenes or objects in 3 dimensions have been around since the advent of radar shortly before World War II. The precision with which you can look at and resolve the scene depends on the technique employed. Radar uses radio waves, which enable transmission over very long distances, but does not allow the measurement of fine detail on the surface of objects. As we change the type of radiation used for looking at the scene, we can start to resolve more detail. Radio waves are meters in length and spread out as they travel, whereas the wavelength of visible light is less than a millionth of a meter and can be much more directional. In real terms, instead of knowing there is a large object at a certain distance, as with radar, we can now think about a system and technique that enables the capture of fine details, even as accurate as seeing 3-dimensional facial features from a distance of a kilometer. But how does this work? Most 3-dimensional imaging techniques rely on time of flight information. What we mean by this is that the time taken for a signal to pass from the transmitter to the target and then return to a receiver is proportional to the distance traveled by the signal. If a certain feature is slightly further away from the transceiver equipment, the time taken for the signal to return is slightly longer. In our custom-built system, the outgoing signal is provided by a laser that sends out pulses of light, each containing many millions of light particles known as photons. The advantages of using a laser in such a time-of-flight setup are numerous. Firstly, the resolution you can achieve in the right, left, up, down directions is very fine, since light from a laser does not spread out like radio waves do in radar systems. The other advantage we can exploit is the use of very sensitive detectors capable of measuring a single particle or photon of light. This means that even if the object we are looking at doesn't reflect a lot of the light that we sent towards it, we can almost guarantee that a few photons will make their way back to our detector and give us an accurate reading of the distance to the point of interest on the object. Another important point to raise here is that since the detectors are so sensitive, we can use a very low power pulse, making the system more eye-safe. So, this enables an accurate distance measurement of one point. But how do we look at an entire scene? The answer is through the use of a simple scanning technique. We aim the laser at a point, record the distance, and then move on to the next point, and repeat this process for the number of points we want to record from a scene. This process is fully automated and computer controlled. After processing the data, we can build up a full 3-dimensional model of the scene or object that was scanned. Here, we see a computer drawing of the system, showing the compact nature of our camera, which takes 3D pictures. Here are the mirrors that allow us to scan the laser across the scene. This lens is used to send out the laser pulses to the target, and then to collect the scattered photons, which are then routed to our detector, giving us the timing information we need to build our final 3D image. With some modifications to the image processing software, it could also determine the speed and direction of the objects being scanned, should they move. This technique can be extended to various other applications, including underwater imaging, where the single-photon detection gives an advantage in terms of range in this highly scattering medium. Also, examination of depth imaging using different colors lends itself to remote sensing of forests, to examine the health of foliage in order to advance our knowledge of the photosynthesis process and carbon dioxide chain. One of the most interesting possibilities is to build up a 3D image of the concentration of greenhouse gases in our atmosphere. This can be accomplished by changing the color or wavelength of the laser used, in such a way that the laser radiation is absorbed by specific greenhouse gases, giving an estimate of gas concentration as a function of range or height. A similar system to what we have demonstrated could be housed in an aircraft or satellite and used to scan the atmosphere below, constantly monitoring the changing atmosphere that surrounds our precious Earth.